Analytical Chemistry 1, Lesson 44. Now there are a couple of situations that can arise that lead to more complicated solubility behavior. They arise when we try to determine the solubility of an ionic solid in a solution that is not just pure water, but instead has other species present already. The two situations we will consider are known as the common ion effect and the complex ion formation. First, the common ion effect. Lead bromide is a sparingly soluble salt. Its KSP value is 2.1 times 10 to the minus 6. When placed in pure water, its solubility is 8.1 millimolar. Now this means that 8.1 millimoles of lead bromide will dissolve per liter of pure water. We can also infer from this result that the concentration of lead 2+ will also be 8.1 millimolar, but the concentration of bromide will be 16.2 millimolar because of the stoichiometry. We can calculate this from the equilibrium expression, knowing the stoichiometric relationship between lead and bromide. S times 2s squared will equal the KSP value. Solving for S gives us the 8.1 millimolar value. So what would happen if, instead of adding lead bromide pure water, what if we added it to a solution that was already 1 millimolar in sodium bromide? Now sodium bromide is completely soluble, so the solution is 1 millimolar in bromide ion before we try to add the lead bromide. To calculate this new solubility value, we substitute S for the lead concentration, but the bromide concentration, when solubility equilibrium is achieved, will be 1 millimolar plus 2S. Multiply this out and find that it produces a cubic equation. Goal-seek can be set up as we've done before, and it readily produces the value S equals 7.7 millimolar. The solubility is now only 95% of that in pure water. What if the sodium bromide concentration is 0.01 molar? Solve the cubic again and find that S equals 5.1 millimolar, which is only 63% of the solubility in pure water. The common ion effect is just a manifestation of Le Chatelier's principle. The additional concentration of product molecules drives the solubility reaction in reverse. The solubility is lower. Here's another example with more complex stoichiometry. The molecule is lanthanum carbonate, which has a KSP of 4 times 10 to the minus 34. First, find its solubility in pure water. The equation is 2s squared times 3s cubed, 4s squared plus 27s cubed, or 108s to the 5th. Substitute and solve for S to get S equals 8.2 times 10 to the minus 8 molar, which is 82 nanomolar. So what would happen if we try to dissolve this in 1 millimolar solution of carbonate? Set up the equation. We have to expand the common ion addition term, which is cubed, and finally we obtain a quintic polynomial. I first set this up in Excel and used goal-seek. It produced a number all right, but I was not convinced. I plugged it back into the original expression for the equilibrium constant under these conditions, and the result should have produced the KSP value back. But it was not even close. It missed by about 11 orders of magnitude. So I went to a more robust mathematical engine, MATLAB. It found the 5 roots. 4 were negative, 2 of them were complex. The one real positive root was this value, and if you plug it in, you get back exactly the KSP. So the solubility decreases from 82 nanometers in pure water to about 316 femtometer, 82 nanomolar in pure water to about 316 femtomolar in a 1 millimolar solution of sodium carbonate. The solubility decreases by a factor of almost 260,000. A common ion can have a substantial effect on a molecule's solubility, but that effect is dependent upon the stoichiometry as well as the magnitude of the common ion's concentration. The common ion effect reduces a molecule's solubility. Now this next process increases a species' solubility. In the next section we will be studying the formation of complex ion, but in this section, even though it's focusing on solubility, it kind of gives away this formation of complex ion story, so I'll try to be brief and to the point. Metal ions are often able to form complex ions. The molecular or ionic species that bind to the metal cation are called ligands. Both molecules and ions can bind in this manner. The ligand is generally donating a pair of electrons, and the metal atom is accepting the pair. Such a bond is called a dative bond. The ligands generally add sequentially to the metal atom, each step being in equilibrium with the previous form of the complex ion and the ligands in solution. The equilibria can be reported as either the stepwise equilibrium constants, the K1, K2, K3, or as the cumulative equilibrium constants. The cumulative equilibrium constants are generally denoted by beta. Note how they are just the product of the stepwise constants up to that point. Either can be used in a systematic approach to solve the overall equilibrium problem. Note that in these reaction equations, everything is the aqueous species in solution, even the neutral species. Even if it has the same chemical formula as the precipitate, it's referring to the molecule that's dissolved in the solvent as solvent water. Now, these additional reaction equilibria draw more of the metal ion out of the solution by providing many new ways it can be found in solution. This tends to increase the solubility of an ionic solid. As an example, consider the solvation of silver bromide. The simple approach we've used so far would note that its KSP is 5 times 10 to the minus 13, and with its straightforward stoichiometry, we know the square root gives the solubility, as well as the concentration of both ions, 7.07 times 10 to the minus 7 molar. This is what happens if we add some solid silver bromide to a container of pure water. But what if we were to add some silver solid bromide not to pure water, but to an aqueous solution of ammonia? So let's say it's 1 millimolar in ammonia. If we were to look up in tables, we would find that silver ion is able to form a complex ion with both 1 and 2 molecules of ammonia. Here are the relevant equilibrium data, which, along with the KSP equation, define this chemical system. We're trying to determine the solubility which is found in the total concentration of silver ions. The difference now is that there are 2 complexes with ammonia for which we must also take account, and in addition to any free silver ions. So how do we proceed? Well, take a look at the mass balance equation. The bromide concentration must equal the sum of all of the silver species. Anytime a silver ion entered solution, a bromide also came along. Even though the silver ends up being partitioned between the free ion and the 2 ammonia complexes, it doesn't change this mass balance. So as always, we seek one equation in one unknown. Replace bromide from the KSP equations and then the complex ions from their respective equilibrium expressions. Gather the silver concentration terms together, solve for silver. Here is an equation involving the equilibrium constants and the ammonia concentration. If we have a lot of ammonia compared to any that is bound in the complex ions, we can just use the formal ammonia concentration. We solve first for the silver concentration, and then, along with the ammonia concentration, we can back solve for all of the other complex species. Sum up all of those silver-bearing species, and the overall solubility is just that sum. This table shows how the solubility increases with increasing ammonia concentration. The first row is for pure water. As the ammonia increases, the free silver decreases at the expense of the growth of both ammonia complexes. Together they indicate an increasing solubility of the silver bromide. The bromide concentration is also equal to the overall solubility. In pure water, the silver and bromide concentrations are equal. Note here, however, that the silver concentration is much lower than that of the bromide, as more and more of the silver that was liberated from the solid is now tied up in the complex ions. At first, the monoammonia species is greater in concentration than the diammonia species, but as the ammonia concentration increases, the diammonia complex ion soon dominates all silver species, and it dictates the solubility. And here's another example that also provides an experimental warning. Silver chloride precipitates with the addition of chloride ions from something as straightforward as hydrochloric acid. Often we are trying to precipitate out as much of the metal ion as possible. We know that when we add an excess of the precipitating counter ion, chloride in this case, that an increasingly larger fraction of the total silver precipitates out of solution. The logical thing to do, of course, is to add a large excess of Cl. And if you do that, you start to find that the amount of precipitate actually begins to decrease. It seems that the old adage that if a little's good, then a lot's better is not at all true. The problem is that as the chloride concentration increases, various complex ions begin to form, decreasing the amount of free silver present in the solution, and therefore inducing additional solvation of the solid precipitate. The solubility of silver chloride increases in the presence of a chloride solution. The solubility is again the sum of all silver-bearing species, and making the substitutions leads to an expression for the silver concentration and hence the solubility. And here is a table of the solubility as a function of chloride concentration. The same trends as before. I've not included the concentration of each species. The dominant species shifts to the one with more chloride as the chloride concentration increases. The amount of free silver decreases even as the solubility increases. Putting the right amount of HCl into the silver-containing solution will precipitate out silver chloride solid, but adding too much will start to dissolve the precipitate again and return silver to the solution, but this time in the form of these various complex ions. When precipitating an ion, be sure to add enough precipitant, but not too much. Knowing what can happen and observing your results carefully will help you to become a successful scientist.